we can calculate the amount of charge on it. Because I know the potential drop or gain, depends on which way you're going, is 12 volts. That's going to be equal to Q times 0.001 divided by 100 times 8.85 times 10 to the negative 12. Whatever that is. Be roughly 1.4 times 10 to the 125. 10 to the negative 6th.
I got 1.062 times 10 to the negative 5th.
Times 10 to the negative 6th?
5th.
5th?
Same.
Okay. Minus 3.
Minus 3?
You lose 3 points if that's your answer.
Coulombs.
Yes. Should have been less of a gap there. Knowing that the SI unit for charge is coulombs, that's really good to know.
I thought you were bragging on yourself for being incorrect. I thought you took off 3 points.
Oh, no. I saved 3 points for you.
Yeah. Took me a second.
My penalty is embarrassment. All right, so we now have the charge, or roughly 10 microcoulombs, 10 or 11 microcoulombs. So we have this relationship here. Suppose now I got my capacitor here, I got my positive charge, and I got my not positive plate and negative plate, and now I stick something in between. If I stick, so I got these two plates, if I stick aluminum foil in between them, what's going to happen?
Gonna go faster. Because it's a conductor.
Therefore?
Therefore, it helps facilitate the movement of electrons.
Okay, how much charge is going to be stored on the plates?
Less.
Oh, we can be more specific than that.
0?
Yeah. Or close enough.
Okay.
Since
Yeah, well, if I put a piece of aluminum foil in between it, those electrons just zipping by. They would not care about the plates at all. All right, so obviously putting metal in between them would not make a lot of sense if you want to store charge. So we stick in the middle something known as a dielectric. Dielectric is just an insulator. So if you hear dielectric, you should be thinking, insulator. Specifically, dielectric is one that is used because of its properties when exposed to an electric field. Before we get into more detail on that one, why on earth would we want to store charge? What is something that we have potentially dealt with? Hopefully, well, it depends on what it is. Where you want charge to be stored. That's more of a storing for chemical reason. That's a chemical storage as opposed to the capacitor.
A light bulb?
Why would you need to store charge for a light bulb?
I don't know. If the power goes out.
Probably battery would be better than a capacitor
True.
for something like that.
Do solar panels have dielectric?
Potentially they do. The solar panel will you get the source of electrons. I'm not quite sure what I guess you would store them on something like that. The advantage of a capacitor, all right, so let's think about it this way. I've got these two plates here, oppositely charged. How can I discharge it? If I got two plates of oppositely charged, how can I get it so I drain all of it?
Put them together.
Yeah, all right. So all I have to do is make some connection here, and suddenly I get this huge flood of charge. So what's the situation in which I want a lot of charge very quickly? This is why I'm not sure about the solar panel, because generally you don't want the charge, all of it at once.
A taser.
That's one of them. Yes. And it's a personal question. Any of you actually been on the wrong end of a taser before?
Thankfully.
My first year, I had a student who had been tased before.
By a cop?
I believe so. It could have been an MP. He's a former Marine.
Oh, okay.
Probably different.
Pardon?
What?
No. He said he peed all over himself. So sometimes it takes a big man to admit something like that. Another place, flash bulbs. I don't know if any of you have dealt with flash bulbs before. Okay, at least two of you. But if you can go on the internet and you can see how to make your own taser. But you get one of the disposable cameras with a flash bulb, and you have to take it apart. But basically, there's a big capacitor in there, so that when you want the flash, you basically connect it. Charge goes through the bulb, so you get the very bright bit of light, and then it goes away because you've discharged it. I do ask, if you ever do something like that, please do not film yourself tasing yourself or other people. There are a lot of videos out there that's been done already. It would just be derivative if you do it, of people building one of these things and going, hey, does this work? Or, come here, little brother.
Is there any other reason why we shouldn't film ourselves than besides it's already been done?
To me, it says, hey, I'm stupid and I'm really willing to let the world know. Yes.
I didn't know that would be illegal or anything.
No, I don't think it. Of course, now when you get the two electrodes, you can have a lot of current going over it. So if on a disposable camera, the leads are about that far apart, when you do it, it's going to tense up all the muscles in between because you got a bunch of current going through the muscles, which could produce a signal to contract. If you do it across the heart, that's when you kill, potentially kill. And so the ones where it's tasers and stun guns. I think it's the stun gun that shoots them out, and the taser is correct. The stun gun, because you have the two leads going out like that, if you do hit on both sides of the heart, that is really dangerous. Now, there's some macho guys out there who go, I can take it, and hit me with a taser. I forget what he sounds like. Sorry, bro. Dude.
What about electric fields?
The electric, I have to look that one up again. I've read about what electric eels do, and I've forgotten. Whether I think that's a chemical storage. That's closer to a battery than a capacitor, but I'm not 100% sure on that. All right, so I stick a dielectric in between. So let's think about what we've done already. I talked about this the other 2 weeks ago, but I have an electric field going this way. It is an insulator, so I'm not going to be stripping electrons off unless I have a large enough electric field here. Now I could potentially put a huge electric field on this and strip electrons off of it, which basically defeats the purpose of the dielectric. But what will happen to the atoms inside here? Well, I'm not stripping electrons off, but what does happen?
You're adding electrons?
Nope, hopefully not. If you're adding electrons, then your capacitor is broken.
So then you're taking away electrons?
Then your capacitor is broken.
Oh, so then you just,
Pardon?
then it's just the same?
No, it's not the same.
Weakening the field?
Say it again?
Sorry, weakening the field because there's something in the way? Or
Not because there's something in the way. I mean, ultimately it is going to weaken the electric field, but the question is why? What is happening to the atoms inside the dielectric that would cause that?
They're repelling the electrons.
Yeah, but the electrons aren't leaving the atom. So what do?
Vibrate.
Well, that's, if in doubt, that's true.
I don't know.
All right, so I have an electric field here,
Restrained, no.
and I've got, let's just take a water molecule. What's gonna happen to the water molecule when it's exposed to the electric field?
It'll polarize. Or it's gonna rotate.
Yeah, it'll rotate. In a dielectric, it'll polarize. Whether it's caused by the atom itself orienting separately, usually it's a solid, so they're not, the atoms aren't gonna orient differently. The electrons will move more likely. But you tend to have, for the atoms here, you'll have, say that's the plus and negative side, so you'll have negative and a plus, and this one will have a negative and a plus. And so you have this, the atoms are polarized, so you have a negative side and a positive side. So this is my atom with its, so that's plus and minus from the external field. And this is negative and plus from the internal field. What's the direction of the electric field created by the polarized molecule? So we have these two electric fields competing against each other. We have the external one coming from the plates, and then we have this internal one coming from the atoms, or the molecules. And so that will overall weaken the electric field inside. It will not completely cancel out the electric field inside. If you could swing that one, I think you are destined to become stinking rich. But it will reduce the electric field inside. Let's think about the effects of that. Ignoring signs. If I'm weakening the electric field, well, what's going to happen there? I got this, if I have this hooked up to a battery, so I know what the voltage is going to be. The voltage is pretty much fixed because it's hooked to a battery. If I were disconnected from a battery, it's a different story. We'll talk about that probably on Friday. But if putting a dielectric in between causes the electric field to drop, there's got to be some offset of that, because that's fixed. That's fixed. So the electric field drops, so suddenly my equation doesn't work. And the equation still has to work.
There's a third variable that we haven't talked about before.
We have talked about it.
So there is a third variable.
It's not going to be added to the equation, it's sort of internal to the equation. If my electric field has to stay the same, but a dielectric wants to reduce it, there is something to make that work. Think about the strength of the electric field.
So it's so would our charge change? Our charge would change?
Be more specific.
Our charge would decrease? Increase?
There we go.
Increase?
Increase.
There you go.
Because the dielectric wants to reduce the electric field. The only way I can keep the electric field the same is to increase the charge. Which means I can store more charge on these plates if I have a dielectric in the middle. So part of the dielectric is so that they can get really close to each other without touching, and the other part of the dielectric is it allows more charge to be stored. And so when there is a dielectric, we suddenly, our equation, based on that over there, becomes Q over A epsilon. There's now a permittivity of the dielectric. Now epsilon sub 0 should be the smallest dielectric that we should ever be able to get. Some people's labs show something else, but it's a physics lab, so you would expect at least one Nobel Prize per lab. So, however, instead of trying to know what the permittivity of every material is, what's the permittivity of paper and so forth, physicists or engineers decided to come up with a shortcut. And they said, if I take the permittivity of a substance and divide by that base permittivity, that's going to be equal to yet one more K. This is known as the dielectric constant. So the lab that you're going to do in 2.5 weeks-ish, you're going to be solving for the dielectric constant. K equals 1 for free space, and then K is greater than 1 for everything else, for non-free space. If it's a conductor, I don't think I've never heard a conductor mixed with dielectric constant, since it's not a dielectric, so. Now air, K for air, is approximately 1, do it that way. So in the lab, we will assume that air is close enough to free space. It's 1.00009, something. That, for some reason, that's sticking in my head. Now, I've talked about all sorts of relationships here when you're dealing with a parallel plate capacitor. There's one other thing that I probably should do before the end of class. Questions to hear before I talk about probably the most essential one for capacitors.
So the dielectric constant is constant only for the material?
Yes.
Not across the board?
Correct.
Okay.
And also I noticed there was a lab that we were doing with parallel plate capacitors before we had the actual plates there, where I just basically cut out 10 centimeter by 10 centimeter piece of aluminum foil, and we were using that as the parallel plates. And in order to get them close to each other, we were basically putting books on top of it and then pressing down to get them close. And it's a valid technique. Unfortunately, one of the textbooks that was being used, and if I can put my hands on it quickly, I was noticing some really bizarre results for two of the groups, and two of the groups had really nice results. But the two groups who had really bizarre results is they were using this textbook as the one that was touching this is what they were pushing down on it. Now, this aluminum underneath the cover here, or whatever, I assume it's aluminum, was not actually touching it because you got a thin veneer there, but basically you have added another layer. You basically have 3 things instead of 2. And so the groups who were doing that were getting bizarre results. And so it was simple enough fix once I figured it out of, stick some other books in there which don't have shiny foil. Now the last big equation for capacitors is capacitance. And unfortunately, again, we have only about 100 standard letters using uppercase, lowercase, Greek, and Roman alphabets. After a number, it's usually coulombs. In context here, it's capacitance. That's equal to the magnitude of the charge divided by the voltage. Capacitance is always a positive number. So if I have some charge Q here, and then some charge negative Q there, it's just the magnitude of one of the plates. You're not adding the plates together or doubling the charge there or anything like that. It's just Q divided by the voltage between them. So in our scenario here, our capacitance would be, so that capacitance right there would be 1.062 times 10 to the -5th coulombs divided by my voltage, which was 12 volts. And yes, once again, this C and that C do not mean the same thing.
8.85 times 10 to the negative 7
Units?
coulombs per volt.
Which is too much for physicists to write, so they came up with a one-letter thing, 8.85 times 10 to the negative 7th farads. Farad.
Okay.
Named after,
Farad.
no, it's actually one of the few that's not named, his name is not Farad, but it is based upon a person. Did somebody say it and I just missed it?
The ferret.
Faraday.
Faraday.
I was close. The ferret.
I've heard a couple people cough today besides me. I'm assuming whoever is coughing is the one who gave this to me. If there's any problem on the test that seems a lot harder than it should be, this is payback. Just so you know.
In my defense, I wasn't here Friday to give you what my mom has, which is what I think I have, so.
Because the incubation period is only a day.
Okay. Never mind then.
So, bringing germs to the classroom, really?
Would you rather us miss class?
I know, when I was growing up, you went to school sick.
Can you do a Morgan Freeman voice right now? With your voice.
Does he have a catchphrase? Oh,
Just kidding.
the easy reader for free space. That's how I know Morgan Freeman. That's my first introduction to him. But later on, when he actually started acting in movies, I thought, oh, that's the guy he was the easy reader from some like electric company. Get you.
The electric company is awesome.
Oh, it's still on? Or was at least when you were younger?
They have a new version that's still on, but I've seen old episodes.
Okay.
Because I wanted to compare the two.
The new ones probably don't have Morgan Freeman.
No, sadly not.
All right, so it's about time. So it's gonna do Don Cornelius, but may he rest in peace. Oh baby. Lab on Wednesday is, yeah, there's nothing to print out on that one. If there's anything to print out, I will supply that for you. I'm gonna be pulling some questions from the book.
I don't have a printout for the lab on Wednesday.
Nothing for you to print out. If you have a PDF of the book or some vehicle for access to the book, please bring that. But there is a plan B if you don't.
Is plan B, is this one?
Plan B, there are just a couple pages that you would need, so I'll print those out for you if need be. And then we have lots of resources over there for the information.